Okay, well, welcome back to class. These video lessons will obviously be a work in progress as we go. So any issues that you guys have accessing them or seeing them or understanding what I'm talking about while I'm discussing this content, please don't hesitate to send an email, contact one of us, either Mr. McDonald or I, so that we can help to make these better quality. So hopefully you can follow along okay. The goal is on all these lessons is to make sure that each video is under 10 minutes long. So there will be lots of smaller videos that are created. So once again, if any individual video is having issues, please make sure that we understand that. Okay, so right before spring break, I know several of you were absent with field trips and so on and so forth on that day. So we are going to begin basically where that lab that we did left off. I know several of you did not get to do the lab, so we will end up going through this lesson. So half of you probably have already seen this content. We can explain this in a little bit more detail, and you'll have this video at your disposal. Okay, so Unit 8, we are going to be discussing the first half of the unit. Is dealing with ideal springs and mass spring systems, and some of the problems will have non-ideal springs. So the first thing we need to do is to identify that term. An ideal spring is one that has a negligible mass and conserves energy, so there's no dampening effect. What that essentially means is that the ratio of the force to the stretch or compression distance of the spring stays constant. Okay, and we'll talk about what that ratio means here in just a few seconds. Also, when we're talking about conserves energy for an ideal spring, this is just another conservative force that is acting on an object as the spring compresses or decompresses. What that means is that we can apply this to all of our energy conversions and our energy forms with gravitational potential energy, kinetic energy, and so on. Okay, so an ideal spring, there is going to be no dampening effect whatsoever. So basically, as the spring stretches or compresses, the force and the stretch distance stays at a constant ratio. Okay, so speaking of ratio, Hooke's law for an ideal spring says that the force from a spring is equal to kx. All right, so the x in the equation, first of all, we need to identify it, is the stretch or compression distance. This is not the length of the spring. So we need to understand that any problem that gives you spring length, you will need to be able to identify what the stretch or compression distance is to fill out the value for x. The k value is what is called the spring constant. The spring constant for a spring has a unit of a Newton per meter. It's not on the notes, so you'll need to understand that. This is a value for that spring. So every ideal spring has its own spring constant. So you'll also notice on the equation, on the second one, it has a negative in front of it. The equation sheet for the AP, I think, does provide the negative, and the AP does typically ask questions about this. This is not a direction as we are used to putting vector notations on it. This is to simply indicate that the spring is always going to return back to its non-strained state. So if the spring is compressed, the force from the spring is in the opposite direction as the force applied in order to compress that spring. If the force is stretched to the right by you, then the spring force is going to be to the left. So the negative does not indicate right, left, up, down. It just indicates that the force from the spring is in the opposite direction as which it is stretched or compressed. Okay, I'll get into this equation here in a little bit. But when we compress or stretch a spring, so if I load an object up on a spring and I compress it, I have to do work to stretch or compress the spring. Okay, but at the same time, if I release the object, the spring is going to decompress and then launch the object across the room. So that means that the spring also does work on the object once it is fully stretched or compressed and then relaxed. I'll derive this equation out here in a little bit, but work done by the spring is equal to a change in the spring potential energy, which has an equation of 1/2 kx squared. Now, notice the work equation is when there's a change in the spring energy. So it's 1/2 k x initial squared minus x final squared. The reason that is important is sometimes it gives the equations, or sometimes it gives the values for the stretch or compression distance and says that the spring is compressed from this point to this point. So you need to understand that x initial minus x final, you can't just subtract those two and then square them individually. You need to, or square them all at once. You need to square them individual as they show in the equation. Once again, pay attention to how the question asks for work done by the spring. If the question says work done on a spring or work done by the spring, those are the same magnitude, but one of those values is going to be positive and one of them is going to be negative. So for example, if you compress a spring, you're doing positive work on the spring's actually doing negative work in that situation. But if the spring expands after you compress it and launches an object, now the spring is doing positive work on the object and the object's gaining kinetic energy. So, speaking of energy, the energy stored in a spring is just simply 1/2 kx squared. So if I ask for, just like gravitational potential energy versus work done by gravity, if we say gravitational potential energy is just mgh, but we say work done by gravity is mg times h initial minus h final. So something actually has to move for work to be done, but we can store energy in the spring just by simply compressing it or relaxing it, or stretching it, sorry. All right, so speaking of the equations, because I've only got a few minutes left here to go into this. When we are looking at force versus stretch distance graphs, the slope of a force versus stretch distance graph for an ideal spring, so notice this is a perfectly linear slope. So this is just following our linear equation of y equals mx. So if we sub in the values for this, we can see that y-axis is force, x-axis is the stretch or compression distance, x. That means the slope is going to be k, since our force equation is force equals kx. The area under the curve, this is still a force distance graph, so the area is still work. So in order to take a spring and stretch it to this distance x, we have to apply so much force to it, so much work is going to be done. So the area under the curve is still the work, and work is force times distance, if you guys remember from earlier in the year. So area is force times distance, and since it's a triangle, it's 1/2 force times distance. If we sub that in 1/2 F times x for base times height, and we sub in our force equation of kx into that, we get an equation that says 1/2 kx times x, which is 1/2 kx squared. So that's where the 1/2 kx squared equation comes from. It's actually derived out from our original force times distance equation that we learned way back in Unit 4 before Christmas break. All right, so once again, this is all work energy equations, so we can apply these to several different sample problems that we've already seen, moving objects, so on and so forth, okay? Because remember, work energy theorem says that the work is equal to a change in kinetic energy. So we will be able to apply this to all of those types of problems as well. All right, so that concludes video number 1.